Okay, great. We did a fun demo, told a fun story, got some good applications. Let's go for a hike or something, or whatever you do in Aspen. Well, yeah, but hang on a minute. There are a couple of small matters left. I haven't really told you what is light. I haven't really told you what is this color content that I keep talking about. I haven't really told you what this tuning is all about. It's just a metaphor so far. And mathematically, there was that crucial relation that had that mathematical property of linearity. I didn't tell you where that came from or why it should be true. I didn't tell you where those sensitivity curves came from and how you could measure them. I kind of snookered you so far. Can we learn something more specific about light and about our eyes? And if so, might have some practical value. That seems to be how it works. Well, the minute you start poking into nature, you start finding things that don't seem right, things that don't fit. What happens, we can detect very dim light, but when the light gets very dim, then your detector stops working, isn't able to see it. As technology increases, though, we've been able to invent gizmos that are extremely sensitive to light, and now we see something disturbing happens when you send them very dim light. Okay, here's the output from a avalanche photodiode. This is time, and this is the voltage coming off that thing. If I give it super dim illumination, I see noise, 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 blip, noise, 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 blip. I see these great big honking blips on top of the noise. If I crank the intensity of the light up a little bit, I don't see bigger blips. This is slightly brighter light. I see the exact same blips, but just a little more frequent. That's not what we expected light to be doing. Light seems to be lumpy. Okay? Long before this, Albert Einstein, also a guy ahead of his time, was forced to that conclusion in 1905. Something doesn't fit in the older picture of light. What are we going to say about that? Now, you may be saying, hey, hold your horses, Phil. That doesn't mean that the light is discontinuous. You go to any water park and you'll find this device, your water pours continuously into it, and it goes dump, dump, dump. Something continuous comes in, and out come these clicks, like those little blips that I showed you before. Doesn't mean that light itself is discontinuous. It is discontinuous. Yeah, well, that's true, but think about it for a minute. That thing, if I take care to send in water at a uniform rate, then that thing is going to go click, 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 click at a uniform rate. It's going to give uniformly spaced clicks. And that's not what those graphs look like. They look kind of random. Now, one popular way to get information off the apparatus and into your brain is visually. You make a graph and you look at the graph. Our visual cortex is good at deciphering spatial relationships. It's a good way of getting, but it's not the only way to get data into your brain. There are other routes into your brain. There's the auditory cortex as well. If this was true, then I could just put a loudspeaker on that detector, and I ought to hear something like this. Okay, it's a harsh sound, but it's definitely a musical note. It's a couple octaves below middle C. Okay, is that what we get or not? So I asked my PhD student to just turn off the laser in his experiment and just have the detector going with only stray light, and we put it through a loudspeaker. It did not sound like a musical note. That's photon shot noise. That's a signal. That's a series of blips, which is not only random, it's as random as possible for a given average rate. So something about light is not only lumpy, it's also intrinsically random. It's upsetting news for a lot of physicists, but we've learned to get used to it. Now, lumpy character of light brings out another interesting feature. When you get down to very few lumps, here's a guy who set up a camera, normal camera, some lenses, and on the back plane he had a very sensitive detector of light, and he illuminated the subject very dimly, and out comes this random collection of dots. You might think it's a map of the sky or something like that. When he cranked up the illumination a little bit more, he got some more dots, but now you start to see something interesting. There are regions where not so many dots are coming per second, and other regions where lots of dots are coming per unit second. That's how light builds up an image. What we think of as an image, it's not really a continuous distribution of the intensity of light. It's a continuous distribution of the probability of arrival of those discrete random blips. That's what an image is. That's that randomness of light once again. That's not some simulation, that's experimental data. So let's frame a hypothesis based on what we've seen so far. Maybe we could be able to test it. Okay, light comes in lumps. I'm going to start calling them photons. Each of those lumps has a distinguishing quality. It's carrying along with it a number, and that number is its spectral color. Those lumps arrive at random no matter how hard you try to make a steady light. That thing we call brightness is the average rate of arrival, the probability per second for them to arrive. That color content, that light spectrum I was telling you about, is just a list of those average arrival rates for each type of lump. There's the rate at which the red ones come, and there's the rate at which the green ones come, and so on. That's the meaning of the light spectrum that I've been talking about without defining it in this talk till now. And an image is just a spatial modulation in those average rates. I'm not done. Let's start talking about vision, our eyes. I want to add some points to that. Some single molecule in a photoreceptor cell can flip like a toggle from one shape to another when a photon comes by, absorbing it. There's precedent for that sort of thing to happen. When baby's born prematurely, he's got too much bilirubin, you stick him under a blue light and it flips all those bilirubin molecules. Or the photon can pass right by without any effect on the molecule or on itself, and it lands someplace else. The choice of whether that photon gets absorbed or not is random, but it has some probability. It's not 50-50, it has some probability. And what is that probability? The probability to be absorbed depends on what kind of molecule. Is it a little one or a big one? There's that size thing we talked about before. That's where the tuning comes in. And also, what was the color of that photon? That's what I mean by the sensitivity curve. It's that list of probabilities for any particular molecule, the probabilities for each different color of light to get absorbed and make it flip. It's just a hypothesis, right? I haven't proved it to you. Those three kinds of photoreceptor cells, each one is packed with billions of just one of those three kinds of sensitive molecules. And then there's some apparatus inside that cell that counts, an integer. It counts how many molecules flipped in a given instant of time and reports that to the brain. That's my light hypothesis, based on things we've seen, but there's some extra things that definitely are crazy. So there you go. I've answered all those vexing questions, but with a lot of new and crazy ideas. Better have some experiment that could confirm or destroy a theory like that before I go about claiming I know something. And right away, before we even do that, you could object. You could say, well, even if it's true, this photon stuff, it can't have anything to do with our eyes. When you work out the numbers, you see that each one of those photons carries an inconceivably small amount of energy, many orders of magnitude less than what you get when you drop a grain of sand on your hand, and that's the smallest thing your skin can detect. How could your eyes detect anything that small? It's very unlikely. It's like Calvin here, Calvin's got an interesting idea, but he doesn't know that brain waves are much too weak to be detected by a colander on top of your head. But, it may be implausible, but if you've got slightly better night vision than the guy next to you, that gives you an enormous evolutionary advantage. You might be able to eat that guy, or you might be able to avoid getting eaten by that guy. Okay? There's a huge evolutionary pressure to get as good night vision as possible. Nature will have tried very hard to go all the way to the absolute limit of sensitivity, and by the way, now we know there is an absolute limit of sensitivity. If light comes in lumps, there's nothing between 0 and 1. The absolute limit of sensitivity is 1 photon. It sounds unlikely, but maybe we ought to look into it and see whether our eyes are that good. Then along the way, we'd get a little, oh yeah, by the way, Calvin, he does have a key idea. I want to keep my ideas grounded in reality. So do we. So let's think of some experiment. We got to make a prediction, and it's kind of weird kind of prediction. So let's suppose our rays really could respond to individual photon absorption events. Seems crazy. So if we place a photoreceptor cell in total darkness and give it very dim flashes of light, that light hypothesis predicts there must be some unavoidable randomness in its response. And I made a little simulation here. Each of these little dots is one of those photosensitive molecules. They're in a big stack inside the photoreceptor cell. And each one has a certain probability per unit time of going flip when I give it the flash of light. And, each one, some random pattern of them gets flipped. If I run that simulation again with the exact same flash of light, landing on the exact same photoreceptor cell, since it's probabilistic, we won't get the same answer. Okay? Different photoreceptor cells get elected, molecules get elected, and furthermore, the total number is also different. That's going to result, according to our hypothesis, in a different signal getting sent to the brain. I can do it a third time, same simulation, same sensitivity, same intensity of the light, and this time we got a different number. Every time we get a different number. What kind of prediction is that?